physics allow to certify genuine randomness, a concept which might be very useful for our society but also very difficult to grasp. To do so, in theory, you only need to perform a Bell experiment, an experiment between two observers, Alice and Bob, in which the correlations between their outcomes and measurement settings violate a Bell inequality. When a Bell inequality is violated, the correlations are said to be non-local, and genuine randomness is certified because the outcomes cannot be predetermined in advance. Now, since a Bell inequality only involves correlations between the outcomes and the settings, the measurement processes in the experiments for Alice and Bob do not need to be entirely characterized. In other words, the violation of a Bell inequality in the absence of loopholes certifies non-local correlations in a device-independent way. So, in this work, we present a general framework to obtain the maximal amount of randomness that a given experimental setup allows for. In principle, our methods could be applied to any setup, but among all implementations, we specifically consider those which are based on a spontaneous parametric down-conversion source with polarization measurements. These setups have recently closed the detection loophole, which is the most annoying loophole that needed to be closed for device-independent randomness generation purposes. Even more, since these setups are entirely optical, they allow for very high repetition rates, and hence for very high amounts of genuine randomness. First, we consider all experimental parameters that can be tuned in these experiments to increase the amount of randomness. Then, by avoiding any binning of the outcomes, and by considering a novel method to optimize randomness over all possible Bell inequalities, we managed to obtain up to 4 times more random bits than previous methods.